Hi guys, I'm Brian Sarpad, a sales engineer here at phoenixNAP. Thanks for coming out. Our friends from Arista are going to give an interactive presentation with some labs, going over some of the technologies that promote their services best. And I'm going to give a quick service overview of phoenixNAP and a little company history. We were founded in 2009. Before that, we actually have our roots going back to 95 as a web hosting firm, but in the data center business, we established in 2009. Right now, we've got 500 employees in a few different offices. Right now, we are an infrastructure as a service provider focusing on data center colocation space, cloud services, backup and recovery, and disaster recovery. We've got 10 data center locations. We own and operate here in Phoenix, Arizona, and the other locations we are a subtenant and leasing space. We have a global backbone that actually ties all our locations together so we can provide transport services. This year we opened up in Frankfurt, Seattle, and Chicago, so we're growing pretty rapidly. We're also Amazon's direct connect partner here in Arizona. So if you need actual private access into the cloud, Amazon Web Services, and you don't want to go over a VPN over the internet, we can actually provide you cross connect directly into their cloud. That's for the Northern California region. And this year we started branching into security services. So we offer a number of services there, including that list: log monitoring, endpoint protection, assessments, incident response. And so that's pretty much it in a nutshell. I'll be around if you have any questions about any of our products, or I can help you arrange a tour after our Arista team presents.
Well, thank you for coming. It's a lot to give up 2-3 hours out of your day, and in some cases drive a few miles. So we appreciate this. We hope that this will be informative and relevant and useful to you. We appreciate the partnership with phoenixNAP. We've been working with them for about a year now, and we've done some interesting things together, and they've been a terrific partner. So we appreciate them being hosts for this event today. So we want to keep this. I'm actually not going to use slides. I'm not going to be up here for too long. But we want to keep this light on the marketing side. Like, we know you guys don't want a lot of product commercials, right? So that's okay. And heavy on the demonstration side with some real-world applications. Mike, our featured speaker, he's going to give some demonstrations and information on things like EVPN, OpenConfig, streaming telemetry. So we want you to see some industry trends in data center that are applicable generally, and in some cases they'll be more applicable to our product, but in other cases we'd like to inform you generally as well. Just quick intros. My name's David. I've been with Arista about 3 years. Prior to that, about 18 years experience in switching, routing, and also a detour to IP voice for a while. Mike has also been with Arista about 3 years, a little over, or somewhere in there. And prior to that, 15 years with Juniper. So he's been doing this a while. And Mike was, I'm going to embarrass him, but he was recently promoted to a manager over our sales engineers. So he's a great resource for us here locally, and he knows what he's doing. So Arista is an interesting company, really interesting company to work for and to just watch from the outside. We shipped our first switch about 10 years ago, so we're not a real old company. We went public in 2014, less than 4 years ago. Over that span, in less than 4 years of public company, our stock and our revenues have gone up about 500% in those not even 4 years. So we've enjoyed a lot of adoption in the marketplace. We've got a lot of momentum as a company. We're doing well. So I guess the question is, why? Are we just lucky, or what are we doing right? What are we doing different? And that's really not what we're here to explore for 2 hours. We're going to dive into streaming telemetry and some of these other things. But I just bring that up if you aren't familiar with Arista. We've really largely redefined what data center switching means over the last 4 years. In a few short years, we've had significant deployments with about 90% of the largest data centers in the country and in the world, including household names that you would be familiar with, like Microsoft and Facebook and Citi and AT&T and Comcast and many others. Locally, we've got significant deployments with GoDaddy and American Express and PayPal, and then a lot of companies that are a little smaller than that. Now we usually don't put Schwab on that list, but they do have a small little handful, so I don't want to leave you out, Philip. And we do a little bit with you guys as well. And I don't go into detail about exactly what we're doing with all these companies because maybe they wouldn't want us to. But sufficient to say that Arista has done well in very large data centers, and we have worked to come down to the large enterprise and the mid-enterprise, which is a little different than a lot of companies grow, or a lot of manufacturers that kind of start small and grow up market. We've sort of done the opposite. So our product areas, what are they? Well, data center switching. We coined the term leaf spine, actually. Also, edge routing. So we have products that compete with Cisco ASRs and Juniper MX, Brocade MLX, et cetera. Tap aggregation has been a nice niche for us, competing with companies like Gigamon and Ixia. Also, virtual routers. When we talk about public clouds or hybrid clouds, we have products that are the same network operating system that run at the edge of that public cloud that can, there's a lot of benefits of having the same network OS everywhere, right? In the public cloud, in the private cloud, and even now in the campus, which is where Arista is going soon. And that's the last thing I'll mention, is we have announced our intention to go into campus switching. And before, we were primarily just a data center company, but now we have acquired a wireless company. We've announced availability towards the end of this year, early next year for PoE switching. So our customers have really pulled us there. Our customers have said, what you do is different, it's better, the quality is different, the stability, the capability, the programmability, it's different. We want you in the campus. And we weren't quite ready to go there until now. We didn't want to rush there and go there too soon. So Arista is becoming a company that competes now in all of those areas. Real quick, our founders, it's worth mentioning, Andy Bechtolsheim founded Sun Microsystems, founded Granite Systems, which became the Cisco Catalyst 4500 platform, which was very successful for many years. He sold that to Cisco. And then if that weren't enough, he was one of the first two investors in a company called Google, and that did pretty well for him, right? So he doesn't need to come to work every day, but he has a passion for this. And he's a really sharp hardware guy, and he's able to see where things are going before they go there. So he is still actively involved on a daily basis with our company. Also, Ken Duda, our CTO, founded Granite Systems with Andy. He's at Arista. He's got, I don't know how many degrees from MIT and Stanford, but a really, really sharp guy. And he's the brains behind EOS software, which is our single image network operating system. And then Jayshree, our CEO, she spent about 15 years at Cisco. For much of that time was the senior VP over the entire data center switching business unit, which was a $10+ billion business unit. So a lot of experience at the top that's driving this ship. We have a relentless focus on hardware and software quality, and this comes from Ken Duda. When it comes to stability and programmability and capability, nobody is ever bonused for getting a certain release out by a certain date. It goes out when it's ready, period. That's our culture at Arista. We auto-test every feature on every release, not just the new ones, because guess what? Sometimes the new ones can break the old ones, right? And so we auto-test every feature. I don't know of anyone else that does that. When our releases come out, they are generally ready, and they are ready for someone to adopt and upgrade to without much worry. And we really are. We consider ourselves a software company. Probably 80% or more of our engineers, their effort is going into the software. So the other component of software quality is the software architecture. We utilize a very different software architecture than our competitors, where running processes don't communicate directly with other running processes. They communicate to an isolated database that exchanges information with agents running that need information from other agents. That's very different than the way our competitors do it, and it leads to a more stable experience. So enough on that. That's not what we're talking about. But if you're wondering, what makes Arista different, that is certainly one of the key things. One of the last things I'll talk about is just merchant silicon. What is merchant silicon? A lot of the switch makers and companies who make routers for years have used proprietary ASICs that they have built in-house. And it costs tens of millions of dollars and in some cases years to develop these. And they need to get a certain ROI out of that. Andy Bechtolsheim, our Google guy, he realized early on that companies like Broadcom and Intel and Cavium and many others, they do this better than us as switch makers can do it. They make chips better, and they were on pace to eclipse what the switch makers could put out in terms of a chip. And also the economics is very different when we allow the merchant silicon companies to make the chips. And so what Arista did, the bet we placed early on that has paid off, is we're going to get the most out of these chips that we possibly can. We throw away their drivers, we write new drivers, and we put the best possible network operating system around these chips. And it so happens that network operating system is a single image for every product family that we have, which has given a lot of advantages as well. So merchant silicon is the way, and most of our competitors have started to follow that as well. You know, we've got robust automation and proactive telemetry that our competitors currently really can't match. And that's what Mike's really going to go into. We have a product called Cloud Vision that provides really what the big cloud companies have developed on their own, like Facebook have developed on their own. We've provided it for you in a very easy to use, turn it on out of the box, and be able to do a lot of config management and automation and integration, et cetera. And that's where our streaming telemetry comes from, is from Cloud Vision. So what we want to show you today is the trend of proactive monitoring, or at least one of the things we want to show you today, rather than things like SNMP polling, where it's reactive and the intervals are not always useful. The polling intervals are not always useful. We can get to a level of granularity with streaming telemetry that's previously unprecedented, and you can do very powerful things with that information in your networks. So that's sort of an overview of Arista and where we came from and where we're headed. And with that, I'll go ahead and turn it over to Mike to kind of dive into some of this stuff and get a look at it firsthand.
The first topic we'll talk about is Ethernet VPN. This is basically how we build data centers. It's going to be one of these primary architectures. So, and it just depends on which one you build is based on how many servers you have, how many compute nodes you have to connect. The simplest is you have a limited set of physical servers, and you can host all those servers in a pair of switches, so you can dual home them. You have enough ports in the largest chassis that we sell, so there's no need to build a two-tier architecture. We call that a spline. Not terribly common, but we do see them out there. Most customers have a need to build, for larger numbers of servers, and they can build a two-level hierarchy. And in this model, you're limited because this is sort of layer 2. One of the requirements in data center is your compute nodes need to talk at layer 2 across racks. So you have to have some type of technology to enable that. A layer 2 design like this one will certainly suffice, so we can scale this higher than the spline, but you still have the limitation of 2 nodes in the center because you can only have 2 nodes participate in a multi-chassis lag. So this one is somewhat limited as well. What we see more commonly is an IP fabric. The more racks you want to build, the bigger this chassis needs to be. The more bandwidth that you're trying to provision east-west, the more nodes you have in the ECMP spine. So we commonly see 4-way ECMP spine for most data centers. Larger customers need more bandwidth east to west, so we see 8-way, 16-way. We have the capability to scale these types of networks as wide as 128-way ECMP. Now, the problem here is an IP fabric, if you have a VLAN broadcast domain in one rack, with a pure IP fabric, there's no way to extend that to the other rack unless you layer another technology on top of it. So you have an IP fabric, you need to have layer 2 mobility across all your racks, you need some type of overlay technology. So typically VXLAN is used in the data center, and as a common control plane, multi-protocol BGP or Ethernet VPN is used to do that. So that's kind of the lab that we're gonna work on today. So for the folks that want to have the hands-on, let me go ahead and get you started on that. You can see that we have the 4 leaf switches and the 2 spine switches, right? They're underneath these containers. The way this works for config management is we break up the config into smaller chunks such that common configuration can be applied at a higher level. So there's certain configs that are applied at the tenant level, certain configs applied to the leaf level, and certain configs applying to the spine level. Anything that's underneath the container structure, so these devices, leaf 1 is under leaf, which is also under tenant. Leaf 1 is going to inherit everything assigned to leaf and tenant. Spine 1 is going to inherit everything assigned to spine and tenant. And then, of course, each individual device has a device-specific config because the IP addresses are unique. Once you do a validate, it compares what's running on the device to what you're going to set it to, and it gives you the delta in the middle. So the idea is to use CloudVision to make sure that you don't have config drift in the environment. So customers can either say, well, I don't want to allow folks to make changes directly on the CLI. So if somebody does go in and make a change on the CLI, it'll show up as a diff. Right? So if this device has config lines that aren't part of the CloudVision design configuration, they'll show up as reconcile lines. And it gives you the choice. Do you want to keep them or you want to just wipe them out? So again, we're going to focus on this. This is kind of our environment. We have a 2-way ECMP spine just to simplify the virtual environment. And we have 4 leaf switches, but we're focusing on leaf 1 and leaf 3. And then there's a host on leaf 1, there's a host on leaf 2. All right, so when we talk about, you guys familiar with VXLAN? One of the issues that you need to overcome is the fact that a layer 2 broadcast domain is typically bounded by layer 3, and layer 3 is meant to keep the broadcasts local to the segment. Now, if I've got VLAN 12, which we do have in this lab, and I want to stretch VLAN 12 to a different rack that's protected by a layer 3 network, I need a way to simulate broadcasts over an IP fabric. So it's considered BUM replication. BUM stands for broadcast unknown and multicast. So we need a way for these top of rack switches, which are sitting at a layer 3 boundary containing a broadcast domain, to look at a broadcast and say, well, if I've got VLAN 12 in another set of racks, I've got to figure out how to get this broadcast to those other racks, because that's the technology that we're trying to enable. So we need a way to do BUM replication. There's different ways to do it. VMware has an NSX controller. You can point all your VTEPs, and VTEP stands for Virtual VXLAN Tunnel Endpoint. Essentially what it does is it takes the entire layer 2 frame, encapsulates it in VXLAN, and transports it over an IP fabric. So we have to have a way to point these broadcasts to some place that's going to replicate them in the right places where they need to be replicated. So there's NSX controller, there's Nuage makes an SDN controller, OpenStack can potentially do this as well. We have a component of CloudVision called CloudVision Exchange. We've been doing this since day one with VXLAN. It's a way to avoid having to go to all the top of rack switches. Can you imagine you have a 100 rack network cluster and you want to take a VLAN and stretch it to all 100 racks? Every time you have a new rack added to the cluster, you would potentially have to go to every top of rack and point it to the other 99 devices in order for it to replicate the traffic. Because we use this mechanism known as head-end replication. Now, you can also have multicast in the underlay. We currently don't support that. So everything we do for BUM replication is all, if the broadcast comes in and we're the head, we have to replicate it from that head device. So if there's 100 racks that have membership of VLAN 12, that head-end device has to replicate it 100 times using IP unicast. But the same data is going to get where it needs to get. So that's what we're doing. Now, the issue that we have with CloudVision Exchange is it only works with Arista products, right? So multi-vendor interoperability is always a concern. So the way that the industry and our customers prefer to do this stuff is to use a standard technology. So you could use a controller. If you're not using a controller, you have to have some other way to do it. And for the most part, BGP Ethernet VPN is the accepted way to do VXLAN control plane. So this is sort of a Ethernet VPN tutorial. We talk about multi-protocol BGP. Are you guys familiar with BGP at all? Anybody using BGP in their networks? Okay, well, good stuff. BGP is really extensible. It's sort of looked on to do many different job functions. With regards specifically to Ethernet VPN, there are these 5 primary route types, and we're going to look at this. If you guys want to play around, you can log into your devices and check it out. The 2 most common are a route type 2, which is a MAC address route. So if I have MAC addresses that live in rack 1 and different MAC addresses that live in rack 20, right? When the top of rack switch sees a MAC address, it sends a BGP update, and it's this type 2 MAC address route. For layer 3 VPN, we have a type 5. So if you hear people talking about, well, what route types do you support? If you support route type 2 and route type 5, you can build L2 VPN networks or L3 VPN networks. Now, they also need a route type 3. What route type 3 does is it basically says, hey, I'm a top of rack switch. I've got VLAN membership in X number of VLANs. This is what they are. And so I can tell everybody else that I'm talking to that if you have some traffic for one of those VLANs, you need to include me. So the IMET route is Inclusive Multicast Ethernet Tag Route, or IMET route. So BGP uses this type of route to advertise the fact that, hey, I have VLANs. I have these VLANs which are part of my environment. If you also have those VLANs, we need to talk to each other. Does that make sense? 1 and 4 less common. I think I'm going to skip over them. It's sort of a service provider way to do multi-homing in the data center. We typically like to build MLAG. So if you have an MLAG, you have redundancy to get to an Ethernet segment. That's one way to do it. In the service provider space, they do it a little bit differently. And that's where the 1s and 4s come in. We'll skip over that for now. As far as what you look for on the configs, you guys use Nexus. We got Nexus customers, Nexus OS. Are you guys familiar with the Nexus CLI? Not even Nexus. Okay. I was going to say, because Arista CLI is a lot like Nexus OS. So if you're familiar with, even Cisco iOS. Like Cisco iOS is a little different than Nexus OS, but it's kind of similar. We're closer to Nexus OS than iOS, but we're going to look at the devices. So the first thing we need to do is configure a VTEP or a virtual tunnel endpoint. That's the thing that takes the layer 2 or layer 3 frame and encapsulates it in a UDP frame, which is encapsulated in VXLAN, right? So that's a VTEP. From a BGP perspective, we're going to have 2 different types of BGP sessions. One is going to be in the underlay. So you've got leaf and spine. We're going to advertise our own loopback addresses between the leafs and the spines. And then we're going to set up a multi-protocol BGP session between those loopbacks. So we're going to have, between the leaf and the spine, we're going to have one session for the underlay, and we're going to have a separate session for BGP Ethernet VPN. And so that's the overlay. So those are the 3 things that we're going to look at. If you look at the config, and while I'm going through these slides, feel free to connect to the devices and look through the config. You can do a show run, and it'll just pick up the whole config. You can bounce around. But essentially what we do is we configure a unique IP address for loopback 0. That's always unique. There's a configuration for loopback 1, which if it's an MLAG pair, both of those switches loopback 1 needs to match. The loopback 0 is always going to be unique at the top of rack. If you guys are familiar with the way you build data centers, you either have a single attached server, or most of the time you have a dual attached server to 2 different top of rack switches that are in some type of arrangement. Cisco calls it virtual port channels or VPCs. We support a technology known as multi-chassis lag. So if you're dual homing servers to Arista top of rack switches, we call it MC lag, and we share the same IP address for loopback 1, such that anybody that needs to get to any servers connected to that pair of top of racks, it can go to either top of rack. So both of them will receive traffic for 1111 or whatever the loopback 1 address is, and both of them can forward directly to the server. Now another interface you may notice is VXLAN-1, and you notice we have VXLAN source interface is loopback 1. So this is how BGP knows that when I send an update, and it's a MAC IP route, that the next hop is going to be whatever I specify here as the source interface. So in our case, it's loopback 1. For leaf 3, loopback 1's address is 3.3.3.3. That you'll notice. This is the default port for VXLAN, 4789. If you look at your configs, there'll be additional information below this, and that's the VLAN to VNI mapping. So in the VXLAN header, we have to have a unique identifier for each VLAN. So VLAN 12, we have configured to be VNI something. I think it's 1200. If you have 4,000 VLANs in a rack, which is potentially you would have to have 4,000 unique VNIs. So the IP fabric needs to know about the uniqueness of the VLANs at layer 2 for each rack. So that's where the VNI mapping comes in. This is kind of what I just talked about. This is really exactly the setup that we have in the virtual environment. We have a single home VTEP1 and we have a single home VTEP2. It's actually 3, right? They can be MLAG pairs in our lab. In this case, this particular lab, one of them is shut down. So we only have the connection to VTEP1 and VTEP3 from the host perspective. And then there's 2 ways at the spine layer to get between each leaf rack to the other leaf racks. It's a 2-way ECMP. So more on the config. The BGP section. So this is focusing on, it looks like leaf 3. So the router ID is, actually this is different configs. I think the AS numbers are the same for you guys that are looking, but regardless, you have some type of AS number configured. Your router ID is typically your loopback 0 address. That's what we recommend. Max paths is the number of ECMP paths that you want to support. You're going to have, at the top of rack, if it's an MLAG pair, you're going to have a peering relationship between those 2 devices. That's this MLAG peer group. And then you're going to have a peer group called spine, and all your spine devices are going to be part of that peer group. And in this case, we specify the neighbors for the MLAG peer group, and we specify the 2 neighbors for the group spine. Redistribute the connected routes. We want to, at a minimum, advertise our loopback because, again, the loopback 0 is going to be the session for Ethernet VPN. We're redistributing the loopback for so you don't have to do it this way. This is the way we recommend. But if I go back to the previous diagram, in the MLAG case, so we're peering the underlay, so straight up family IPv4. We're peering between the link addresses, one here and one here, so two underlays. This guy also has an underlay peering association. So this was the group MLAG peer between these 2 devices. And then each of them have the 2 spines in the spine peer group. Their function in Ethernet VPN is to advertise their loopback 0 address. So we have a loopback 0 to loopback 0 address peering relationship, loopback 0 to loopback 0 here. Now, for the communication that really needs to happen is for all the VTEPs to be able to talk to all the other VTEPs. So in our simple environment, it's just rack 1 and rack 3. When you have a 100 rack network, you'll have 100 racks worth of peering. And if you had to build a full mesh of all the leaf racks to all the other leaf racks, it would get pretty ugly pretty quick. So instead, what we do is we just create a hub and spoke between the leaf racks and the spine racks, and the spines basically act as transit for leaf-to-leaf traffic. So we basically have a lot less sessions, and that's how we do it. So it's eBGP multi-hop. I think part of your question was, well, it's a direct peering relationship. It's not. I guess it's not really it looks like it's point to point, but we use eBGP multi-hop. When I first heard it, I'm like, okay, so I'm actually peering leafs to other leafs through the spine. Not really what we're doing. The reason we have to be multi-hop because it's the loopback. It's considered one hop to get to the link, and then another hop to get to the other guy's loopback. So it's eBGP multi-hop, but it's just between loopback 0 of the leaf and loopback 0 of the spine. So we avoid having to do leaf 1 switches to 99 other peers. We only do it to the number of spines that we have. So in the lab case, it's 2. In most networks, it's 4. So it's a lot easier to manage that. All right, so that's the underlay config. As far as verifying, this is kind of what I was doing before. If you want, you can do this as well on your setup. If you look at leaf 1, show IB BGP summary, it's going to show you the fact that you have 2 peering connections and they should both be the spines. Now let's take a look at the overlay. So I just was talking about this a bit. The way the overlay config looks like, we have another peer group. You could call it whatever you want. We typically call it, I usually stick EVPN in the name just so I know it's going to be the peer group that's exchanging the multi-protocol routes, which are family Ethernet VPN. We do this thing called next hop unchanged. So that's how we're able to peer between the leaf and the spine, and we really care about the routes that are coming from the other racks. So all the other racks also have, for VTEP 3, he's announcing routes this way to the spine. There's a session here, and then there's a session here as well. So when VTEP 3 says, I have all these MAC addresses that live in my rack, send it to the spine sends that same data to VTEP 1. Now, normal rules of eBGP would say that I'm going to change the next hop to my own address. The reason we use next hop unchanged is because we really care about sending traffic from VTEP 1 to VTEP 2. That was those two addresses, loopback 1 and loopback 1 on the other side. It was 1.1.1.1 for all the MAC addresses that are behind VTEP 1, and it was 3.3.3.3 for addresses that were behind VTEP 3. So to take advantage of the fact that we don't have to mesh all the VTEPs directly with each other, we just peer them through the spine. The spine says, all right, I'm going to re-advertise those routes, but I'm going to keep the next hop, the original next hop. So when he says, all right, I need to get to any of these MAC addresses, he knows he's got to send it to 3.3.3.3 and not his loopback address or his link address. Does that make sense? You're going through the spine, yes. And that's why I think they picked transit, because you're kind of transiting through the spine. So we're not changing the physical structure of the leaf spine network, right? You still have a link to every spine. So from a traffic flow perspective, you're still going through the spine. There's no, unless you physically connect all your leafs to each other. All right, verify the overlay. So this is some of the commands we've been doing. So show BGP EVPN summary, and then show BGP EVPN, and then you could do route type, and you're going to see IMET routes, and you're going to see MAC IP routes. So for this lab, those are the only two that are there. If we were doing layer 3 VPN, you'd see some type 5 routes. It would look just like a regular IP route. This is kind of, it gives me a visual anyway to talk through. What happens is, we've got our VLANs. This particular diagram calls it subnet green. It's 10.10.1.0/24. In our case, it's 172.16.0/24, if I'm not mistaken. It's whatever subnet is configured on host 1, and leaf 1 and leaf 3 have a VLAN 12. So the broadcast domain is stretched. And again, I mentioned this earlier. There'd be a VLAN to VNI mapping. That's what happens in this environment. We need to uniquely identify the layer 2 domain over an IP fabric. So in this simple example, we have 2. In our lab setup, we just have the 1. And this gives us the ability to stretch that VLAN to as many IP endpoints as we want. So what happens when a device has traffic to send? Typically, this guy is going to want to send to somebody. He either knows who he's talking to. He might be ARPing for his gateway. He might be ARPing for another device that's on the same segment. In any case, when the top of rack switch sees traffic with a MAC address in the source, just like a bridge builds a table based on the source MAC address, he sees it, he builds an entry and says, okay, this MAC address is out this physical interface. And by the way, I've got to send an update to everybody who has VLAN membership in VLAN 12, or in this case, subnet green. It tells everybody where that MAC address. So the next guy looking for that MAC address, he can just send a direct update right to the VTEP. Standard MAC aging. So if I don't see any traffic from a MAC address in a certain amount of time, it's going to drop it from the table. This is what I just talked about. Locally learned MACs are automatically redistributed to all my other VPN endpoints. And this is an Arista specific limitation. In the route type 2 update, you can include just the MAC address, or you can say, I also want to tell you what IP address is at that MAC address, so that you can learn both of those things, communicate that throughout the environment, and when you see an ARP request for that IP address, you don't necessarily have to flood, you don't have to BUM replicate the ARP address. You can say, hey, I know where the IP address, it's at this MAC address. It's a feature called ARP suppression. Currently, we're not doing that. We should be adding that shortly, but that's the point that we're trying to make here in the route type 2 update. You can just send a MAC, or you can send a MAC with the optional IP that lives at that MAC. So you basically have both layer 2 and layer 3 information. We talked about dual homing. So again, this is the diagram for what I was talking about. When these are two top of rack switches. This is a host, He's got a port channel. He thinks he's talking to one device. It's two physical devices. This is an MLAG. And basically, we're saying VTEP1 is associated with loopback 1. And it doesn't matter which one of these two switches receives traffic. They both own that shared VTEP. They both can forward the return traffic back to the MAC address. I think that's fairly straightforward. So what is the rest of the config in BGP look like? If you guys have done a show run, so far we looked at the underlay section, then a little further down was the EVPN section. You might have seen some stuff for address family. There's what we call a MAC VRF. So underneath the router, there'll be a section that says, hey, for this VLAN, I need to configure more information that multi-protocol BGP needs to communicate the existence of this layer 2 information over BGP. So underneath that, we have this thing called a route distinguisher. You give it a number. Typically, I recommend the loopback 0 address. This happens to be the loopback 1. It doesn't really matter. I just like the loopback 0 because I want to know which guy sent it. Right? If I use the loopback 1, I'm going to get 2 advertisements that both have the shared loopback 1 address. And then this thing is this is an identifier that's unique to the particular VLAN. So typically, I suggest that you match the VNI. So VXLAN VNIs are 24 bits. So the total number is like 16 million, right? In VLANs, you only have 4,000 because of the number of bits that you can use to represent a VLAN. Most customers don't have more than 4,000 VLANs, so I typically recommend that whatever the VLAN number is, in our case 12, I would map VLAN 12 to VNI 12. They didn't build a lab that way, and that's okay. They don't have to match. I just typically recommend it. So from a route distinguisher perspective, I typically recommend loopback 0 : VLAN VNI number, right? And then you also configure a route target. That's an extended BGP community that says to the other guys that are speaking Ethernet VPN to you, it just says, if I see this route target, I know which MAC VRF it's intended for, so I'm going to import that into the appropriate MAC VRF. And then this redistribute learn, that's what handles the redistribution of MAC addresses that are learned on the local interface over BGP. So those are the config states. Really, I mean, there's not a whole lot to it. So type 3 is the IMET route. Again, it stands for Inclusive Multicast Ethernet Tag. Basically, it's meant to tell you all the VLANs, route distinguishers, and route targets that live on the other guys so that you know if you have matching VLANs and whether or not you should flood traffic to them or not. Or forward in a unicast fashion if it's just a unicast traffic. So MPLS can be the tunnel technology. You know, the fact that you need to take a layer 2 frame and put it in IP or put it in something in order to get it somewhere else over a non-broadcast type of medium, which IP fabric is, you need some type of tunneling. So it's more common to be VXLAN, so that's what the tunnel type is. Thought I'd show you just one slide for layer 3 EVPN. It's very similar in the way it works, except that for the update, so this is an EVPN network update. You just have instead of a 2 and a 3, you would have a 5 and potentially a 3 for an IP prefix, and then the substance of that type 5 route. What's different is you have a prefix length. It's 0 to 32 for V4, 0 to 128 for IPv6, and then you actually have the prefix. So the technology exists to do layer 3 VPN with Ethernet VPN. Customers build pretty wide networks. I believe our sys-test team tested to 300 racks. So doing head-end replication to 300 racks is not a problem. So if we had an ARP request and that VLAN lived on 299 other racks, they've tested that environment and it's not a problem. So some people say like, well, why would I do head-end replication when I can do multicast and it's sort of more efficient, right? I can send a multicast frame out and then all my leaf racks join the same multicast group. Yeah, I mean, you could do it that way, but it's another control protocol that you have to deal with. So I mean, all the forwarding happens in the chip. So Broadcom, primarily our products are built with Broadcom chips, and they don't have a problem forwarding traffic at line rate, essentially to a large number of destinations. So not a problem. Most folks don't build 300 rack pods. Our biggest customers certainly do, like Facebook. Facebook builds like 280,000 servers per pod. So not only do they build a 2-level N-way ECMP, they build it 4 levels. So they get their top of rack switches, which are their own, because they've got hundreds, thousands of them, but they use our chassis in the next 3 levels, and so they build a cluster that's gigantic. Microsoft Azure's built with us as well. So for the heavy lifting, these guys use our switches because of the way they scale and the reliability of the code. Just wanted to talk about OpenConfig as a technology and demonstrate that Arista has OpenConfig solutions. So because obviously we'd love it if all our customers bought CloudVision. Our biggest customers do automation on their own. CloudVision was designed for customers that either have a limited staff that can do automation or they don't have any staff that can do automation. So when I worked at Juniper, if Junos didn't support a certain feature, basically the answer was, well, you can do that with the SDK, and it's an API, and if you have programmers, you can write your own program, leverage the SDK, and you can do some unique things with the software. Not all customers, most customers don't have that, especially in our territory. So Arista is the first company that I've worked for that has not only a great set of APIs on all our devices, but we actually deliver applications that can leverage the APIs. So CloudVision was designed to support complete turnkey automation for the full life cycle. So you rack a device, you power it up, it's ZTPs from CloudVision, and it automatically can assign all the config. You can do image updates from CloudVision. You can do change control, and you can do telemetry. So it's sort of an all-in-one. We give you all the apps that you need for automation using CloudVision. Our biggest customers have staff to do automation. They don't want to buy a product from every vendor to do their whatever it is they want to do, whether it's network change control or whether it's telemetry data. So they look for an industry standard way to do this. So from a telemetry perspective, we're supporting 2 tracks. You can get all the telemetry data using our own agent that runs on the box, and it'll give you all the state, and it'll stream it to a database, whether that database lives in CloudVision, our application, or whether that database lives on your own homegrown built backend, right? We don't care. If you have the skills to build your own backend and have application level programmers who can look at the data and present it in meaningful ways, then we say, God bless you, and happy to have you do it. So Terminator is an agent that subscribes to all the state on an Arista device. Where OpenConfig falls short, OpenConfig is meant to be an industry standard. So if we look at, take these building slides, I'm just going to skip to sort of where it's coming from. This is representing all the state. So as I mentioned, if it's an Arista switch, you can run our agent, which subscribes to everything, and as there's a change, it streams it off the box to either CloudVision or some other backend that you might be building yourself. Our big customers say, well, I'm not going to buy CloudVision. I want some industry standard way to look at this data. So the big guys that are out there, the operators, so this OpenConfig consortium, if you go to openconfig. I think it's net, you'll see that there's a collection of, we call them data models. So this concept, YANG, represents a structure for information. For example, I think the first one that the guys like AT&T and Verizon, Comcast, Google wanted was, what do they change on a regular basis, and how many different router vendors are in their network? Well, it's usually routing policy. They're trying to figure out, how do I change routing policy to affect the way traffic gets forwarded? And if you have to send config commands to 5 different devices, and they're all different and unique in their CLI or the way you configure them, that becomes a headache, and there's a lot of investment. So what YANG set forth to do is to create a structure that says, hey, if I'm going to configure BGP, the AS number, there's a structure. It's kind of like a schema. If you guys ever play with network management solutions, if you had to work with a vendor-specific management application, you needed to have a schema that management application needed to send config data to that device. So what YANG represents is an industry standard way to configure common parameters on any vendor switch. So if a vendor supports OpenConfig YANG model for BGP, that push is going to look the same for Juniper, Cisco, Arista, anybody, right? So the idea is, as long as there's a YANG model, I can use a YANG model and I can make sure the vendor supports those models, and I can come up with one way to push config data or look at telemetry data, right? It says OpenConfig. It's a bit of a misnomer. And here's the last point. Don't let the name fool you. OpenConfig models also define the way you look at things like interface counters. So the big guys just said, hey, you want us to spend $100 million a year on you, Arista or Juniper or whoever, we need you to support OpenConfig. And guess what? Everybody wants customers to spend $100 million with them. So that's kind of what's driving Arista, Juniper, Cisco to support things like OpenConfig. So, a customer that has their own staff can just write to these YANG models, and they can control many different vendors using the same applications. Does that make sense? So the way you communicate using OpenConfig is one of, it actually can be any. I mean, we actually support 3 different methods for the session, the API session. NetConf, RESTConf, and another one called gRPC, which was sort of authored by Google. It stands for Google Remote Procedural Call, and there's an interface. It's the GNMI, or Network Management Interface. We support those 3, NetConf, RESTConf, and GNMI. We recommend GNMI because it's the most efficient of the 3. And I can show you what that looks like. So if you're interested in seeing what models are available, you can go to this GitHub site. The openconfig.net will also point you eventually to this place. It gives you the structure of all these models. And sort of the challenge is, right now there's a limited set of models. So if you're an Arista customer and you want data that's not yet represented by a YANG model, then you don't really have a choice, but you would prefer to use our agent that streams all the state. That's sort of proprietary to Arista, right? We couldn't take our agent and run it on a Cisco box. If you are okay just looking at data that's represented by these YANG models, then from our perspective, you have a choice. You can either stream it off using Terminator, or you can stream it off using OpenConfig. And CloudVision will eventually support both. Today it only supports Terminator. So if you're building your own backend, you can either listen to Terminator or you can listen to OpenConfig. So we try to give you best in breed choices to do this stuff. This is sort of the specifics about when we started supporting this stuff. So where does that take me on the sort of tutorial here? Just as an FYI, the reason we moved to telemetry, streaming telemetry and OpenConfig, Google Protobuf, the way to take all this state information and stream it off a device in real time is an entire replacement for SNMP. SNMP is polled over some polling interval, so essentially what you're getting is an average of data over an interval. If there's an event that happens between that, you may not get the severity of that event. If you're streaming telemetry in real time, and I'm talking about at a maximum of every 200 milliseconds, we're packaging an update and shipping it off the box. So if something changes within a 200 millisecond window, you're going to know about it, right? So this is just saying this is a real thing. Large Cloud Titan, it's Google, right? There's no secret there. They have absolutely zero SNMP within their network. They're doing complete state streaming in their network. So it's essentially meant to replace SNMP and get you more granular and more useful information. We're saving all this data in a database. So for example, you might have your customers come to you and say, well, I was trying to run this application last Friday and I was having some problems. You can actually take the slider bar and move it backwards to that particular date, and it would show you the data and the hotspots in the network at that given point in time. So it's called a time series database. We maintain the data in telemetry for at least a month, and depending upon what the metric is, we might keep it for 2 or 3 months, right? So if, for example, interface counters, we stream interface counters every 2 seconds. If that data is a month old, we would maybe stop keeping the 2-second intervals and we would only keep the 5-minute intervals. So we automatically coalesce the database based on time. So we can keep the metrics for X amount of time, and it's really only bounded by the amount of storage that you have. When we sell this product as a package, we include a terabyte worth of storage data, and we do cleanups about every month or so. Some data lasts longer than others. It's kind of the point.